All right, today we are diving into one of the biggest, most persistent problems holding AI back. Its memory. Or, more specifically, its terrible memory. We're going to break down why AI agents get so completely lost during long tasks, and then look at a really fascinating new solution. One that's inspired by the most powerful computer we know of, the human brain.
Okay, so let's get right to the heart of it. The folks behind this research call it the unbounded memory problem. Now, this doesn't mean AI can't remember things. Oh no, it's actually the opposite. It remembers everything, all the time. And believe it or not, that's a massive, massive problem.
You've probably felt this yourself, right? You're, say, 20 messages deep in a chat with an AI assistant, you're trying to get it to do something complex, and then bam, it completely forgets a critical instruction you gave it right at the start, or it starts contradicting itself. This isn't just a little quirk, it's a fundamental flaw that makes AI today pretty unreliable for any kind of serious, multi-step job where one mistake can mess everything up.
And this slide really nails the difference. Think about our memory. It's so efficient, right? We remember the gist of a conversation, we automatically filter out all the ums, ahs, and irrelevant chatter, and just hang on to what matters. AI? Well, its default is to remember every single word verbatim. It's like it's forced to reread the entire transcript of your conversation from the very beginning every single time it needs to respond. All that noise just piles up, and it starts making mistakes.
So you might be thinking, okay, but surely people have tried to fix this. And you're right. They have. But the thing is, the current methods, well, they're just not working. They're basically band-aids on a much deeper wound. Right now, there are pretty much two main ways we try to handle AI memory. The first is transcript replay, which is what we just talked about. You literally just stuff the entire conversation history into the AI's prompt. It's slow, it gets ridiculously expensive, and it drowns the AI in information. The other approach is retrieval. This tries to be a bit smarter by plucking out what it thinks are relevant bits from the past. The problem is, it often gets it wrong and pulls out old, stale, or just plain wrong info that confuses the AI even more. And don't just take my word for it. The researchers put it perfectly here. Memory isn't just a small feature to improve. It is the central barrier holding everything back. It's the main reason we can't trust AI agents with really important, long-running jobs yet.
So, if our current computer-based methods are failing, where do we turn for a better idea? Well, it turns out the best model for an efficient memory system has been right inside our heads this whole time.
And this brings us to the breakthrough idea in this paper, the Agent Cognitive Compressor, or ACC for short. Just think of it as a memory controller for an AI that's built to act like our own working memory. So instead of that infinitely growing, messy transcript, it maintains a small, focused internal state. It only keeps what's actually important for the task at hand.
This diagram shows you exactly how it works. The ACC is like a bouncer, or a gatekeeper, for the AI's memory. Information comes in from the conversation, from tools, from all over, but it doesn't just let everything in. It stops, it checks, it compresses and filters everything, and only commits the most vital information to the AI's core memory, what they call the compressed cognitive state. So what does this compressed memory actually look like? This is where it gets really interesting. It's not just a shorter version of the conversation, it's a totally new way of organizing the information. So you go from that huge, messy transcript to this, a clean, structured, and super organized summary. This is the compressed cognitive state, or CCS. You can think of it as the AI's equivalent of a human's focused, in-the-moment thoughts. And just look at this example from a real-world IT task. Instead of wading through thousands of words of logs and chat history, the CCS boils it all down to the absolute essentials. What's the goal? Reduce that 502 error rate. What are the rules? No restarting the server. It's even tracking what it's unsure about. This is information an AI can actually use to make smart decisions without getting lost in the noise.
Now, this all sounds fantastic in theory, but the big question is, does it actually perform better? Well, the researchers put ACC head-to-head with the old methods, and the results? They're not just a little better, they are night and day.
First off, let's talk efficiency. This chart is showing memory usage over a long task. That first bar, the baseline method, that's the old replay everything approach. See how it just grows and grows and grows? Now look at the ACC bar on the end. It's tiny. Its memory use stays small and controlled, which means it's cheaper to run and way, way faster. But here is the real kicker. These graphs are tracking mistakes over a long 50-step conversation.
The chart on the left shows hallucinations, basically the AI making stuff up. The one on the right shows drift, which is when the AI just forgets what it was supposed to be doing. All those other lines for the old methods are all over the place, just constantly making errors. But that green line, that's ACC. It's flat, right down at 0. It stays perfectly focused and accurate for the entire task. It's just incredible.
So what's the secret sauce? How does it do this? The key insight is that AAC separates the act of recalling information from the act of committing it to memory. So just because the AI remembers something from the past doesn't mean that memory gets to pollute its current thinking. Everything has to pass through that smart compression filter first. It's like a built-in fact checker that protects the AI's focus.
So this is way more than just a cool academic paper. Building an AI with a memory that actually works, that has profound consequences for the real world.
A reliable memory is what we need to finally unlock AI for really complex jobs in high-stakes fields. I mean, think about an AI helping a security analyst during a live cyber attack, or helping a doctor sort through a patient's complicated medical history. In those moments, you absolutely cannot have the AI getting confused or forgetting a key detail. This kind of tech is what will finally move AI from being a fun toy to a truly dependable partner.
Because at the end of the day, that's what this all boils down to. It's about trust. By solving this core memory problem, we're taking a giant leap towards building AIs that we can actually trust with important, long-running jobs without worrying that they're going to get lost along the way.
And that really leaves us with a fascinating question to chew on. For so long, the true potential of AI has been bottlenecked by this one fundamental flaw in its memory. But now that we have a blueprint for a memory that actually works, one that stays focused and filters out the noise, what does that make possible? What huge, complex challenges can we finally and confidently hand over to our AI partners? It feels like we're just at the beginning of finding out.
You've probably seen the headlines. The whole software world is buzzing about a totally new kind of AI. We're not just talking about an assistant that helps you with a line of code here and there. Nope. We're talking about fully autonomous AI software engineers, like Devin, that can literally join your team. The hype is off the charts, right? But what happens when these things actually get into the wild? Well, some new research put them to the test, and the results? They're pretty eye-opening. Let's get into it. So, where is all this coming from? Well, this new reality, this idea of an AI teammate, it all really boils down to one simple but game-changing question. The promise here is just huge. Think about it. We're moving way beyond tools that just pop up suggestions inside your code editor. We're talking about AI agents that you can give a task to and they'll work on it all by themselves across the entire project. And then they submit their work as a complete pull request, just like any other human on your team would. Okay, but before we get into the juicy results of this study, we've got to be super clear on the two different types of AI tools we're talking about, because they are fundamentally different beasts. Here's probably the best way to think about it. An AI assistant, like GitHub Copilot, that's your GPS. It gives you turn-by-turn directions while you're still in the driver's seat. It helps you out, but you're still doing the work. Autonomous agents, on the other hand, well, that's the self-driving car. You just give it a destination, and it figures out all the complex steps to get you there. It operates on a whole other level. All right, so with this powerful new tech on the scene, researchers set up this massive experiment. They wanted to see what actually happens when you unleash these autonomous agents on hundreds of real, live, open-source projects. And the way they designed this study was pretty smart. It was all about comparison. They wanted to figure out if these new agents had a different impact depending on whether a team was already using other AI tools or not. So they split all the projects into two main buckets. First up, you had the agent-first teams, or AF for short. These were projects that had never touched an AI coding tool before. They went straight to the new autonomous agent. And then you had the IDE-first teams, or IF. These were the folks who were already used to AI assistants, like Copilot. Now, it's really important to know that these two groups weren't exactly the same. The agent-first teams, they were generally working on smaller, less active projects. But the IDE-first teams were part of larger, more popular projects that had already jumped on the AI bandwagon. And that little detail, well, it's going to be super important in a second. Which brings us to our first big reveal. How do these AI agents affect one of the most important things in software development? Speed. This is the million-dollar question, isn't it? If you add one of these autonomous AI teammates to your project, are you actually going to get things done faster? At first glance, the results looked absolutely insane. the study found that teams using these agents added over 76% more lines of code on average. That sounds like a game changer, right? But, and this is a huge but, there was a major catch. Yeah, that incredible gain, it didn't happen for everyone, not even close. It was almost exclusively seen in just one of the groups, the agent-first teams, the ones who had zero prior AI experience. And when you look at the chart, the difference is just whoa. The agent-first teams saw their code output jump by 77%. But the IDE-first teams, the ones who were already using Copilot, their code output actually went down a little bit. It points to this idea of diminishing returns. It's like once you get that first AI boost, adding another one on top just doesn't give you the same kick. So, that's the story on speed. But velocity, that's only half the picture. Because all that incredible acceleration came with a very real and pretty concerning hidden cost. And this is where the story gets really, really interesting. Because unlike that speed boost, which only helped one group, this next part hit everybody. And trust me, it wasn't good news. Across the board, projects that brought in these autonomous agents saw a nearly 39% increase in something called cognitive complexity. And again, look at this chart. Both groups saw a big jump here. The agent-first teams saw their complexity rise by 35%. And the IDE-first teams, the ones who didn't even get a speed boost, they saw an even bigger spike of 43%. So, what in the world is cognitive complexity? Well, it basically means that AI is writing code that's a real pain for humans to deal with later. It's harder to read, it's way harder to debug, and it's a nightmare to change or build on top of. In other words, it's a one-way ticket to creating long-term technical debt. So what does this all mean for a team that's thinking about bringing on an AI teammate? What is the real bottom line takeaway here? Well, it pretty much boils down to this. Step 1. Yes, these AI agents can give you a massive boost in speed. Step 2, but, and this is a huge but, that benefit only seems to apply if your team is totally new to AI tools. And step 3, for everybody, no matter your experience, these agents consistently make your code harder and more expensive to maintain in the future. You know, the researchers who actually did the study, they summed it up perfectly. They said these tools are powerful but risky accelerators whose value depends on prior AI exposure. So at the end of the day, it all comes down to a single, really tough trade-off. You might get a huge injection of speed right now, but you are very likely going to pay for it later with a messy, more complex codebase. And that leaves us with the final question, the one you really have to ask yourself and your team. Knowing this trade-off, knowing you might be sacrificing the future health of your project for speed today, is the speed worth the debt? You know that dream we've all had about having a robot helper around the house? One that can do pretty much anything you ask it to? Well, for decades, that's been the goal. But it turns out there's this one really stubborn problem that's been holding that future back. And this is the big question, isn't it? It sounds so simple, but for an AI, this is a massive, massive hurdle. See, every time we try to make a robot really good at one specific physical thing, we accidentally make it, well, dumber at everything else. So here's what we're going to dig into. First, we'll unpack what's called the smart robot paradox. Then we'll look at a really cool solution that's actually inspired by our own brains. After that, we'll check out the tech that makes it all work, and finally, see the results for ourselves. Ready? Let's dive in. Okay, first things first, let's get right to the heart of this problem. There's this fundamental tug-of-war going on inside the AI brains that power these advanced robots. So, the AIs we're talking about are called Vision Language Action Models, or VLAs for short, and they are incredibly powerful. They get their start by basically absorbing a huge chunk of the internet, text and images, which gives them this really amazing general understanding of the world. And this is where you can see the conflict in action. On one side, the robot needs all that general knowledge just to understand a simple command like what a coffee mug even is. But on the other side, it needs to be fine-tuned with very specific data to learn the exact physical movements to, say, place that mug on the coaster. And here's the kicker. That fine-tuning process leads to a huge problem with a pretty dramatic name, catastrophic forgetting. Basically, as the AI learns that new physical skill, it starts rewriting its own programming, and in the process, it just erases its original knowledge. The researchers put it perfectly.
The model essentially sacrifices its linguistic brain to gain a robotic body.
So what do you do about that? How do you solve it? Well, to figure out this digital problem, researchers look to the best computer we know of, the human brain. And the answer, it turns out, is right there inside our own heads. They took inspiration from this principle called hemispheric lateralization. It's just a fancy way of saying that the two halves of our brain are specialized. They have different jobs, and they don't try to do everything at once. This breaks it down perfectly. Think of it like this. Your left brain is the what department. It handles the big picture stuff, like language and understanding concepts. And your right brain, that's the how department. It's the specialist that handles spatial awareness and the fine motor skills needed to actually do things. They work together, but they stay in their own lanes.
And that leads to this really brilliant idea. What if we could actually build a robot's AI to copy that same elegant design? What if you could separate what it knows from what it does, so they can't overwrite each other?
And that is exactly what these researchers did. They built a brand new architecture called TwinBrainVLA, and as you can probably guess, it's designed to work just like our own two brain hemispheres. Okay, so let's walk through how this thing actually works. First up, you have the left brain. This is an AI model that's been pre-trained with all that internet knowledge, but then it's frozen. It's locked down so it can't be changed. Then you have the right brain. This one is totally trainable, but it's only focused on learning physical robot skills. Now, to make them talk, there's a special one-way bridge that lets the right brain ask the left brain for information, but it can never, ever change it. And finally, an action expert takes all that combined info and turns it into precise movements for the robot. So this is the whole idea in a nutshell. The left brain is like this stable, unchanging library of knowledge. It's the anchor. Meanwhile, the right brain is flexible. It's always learning, always adapting to new physical challenges, but without any risk of causing that catastrophic forgetting. It's brilliant. All right, so the theory is super elegant, but here's the million-dollar question. Does it actually work? Well, the researchers put the TwinBrainVLA through its paces with some really tough tests to find out. They use this really challenging simulation called RoboCasa. And it's not just simple stuff. It involves 24 different complex household chores. We're talking about things like opening a cabinet, picking up a bottle, putting it inside, and then closing the cabinet door. Tasks that need both deep understanding and super precise control. And the results, well, they pretty much speak for themselves. When they put TwinBrainVLA head-to-head against another top-of-the-line single-brain model, the two-brain version had a way higher success rate. We're talking almost 55% success, compared to just under 48% for the old model. Now, I know a 7% jump might not sound like a crazy number, but trust me, in the world of robotics, an improvement like that is a huge leap forward. Just by splitting the AI's brain in two, the robot became way more reliable and way more effective. And this really gets back to the core of the breakthrough. The researchers themselves say that this new design structurally immunizes the model against that knowledge loss we talked about. It's not just a slightly better way to train an AI, it's a fundamentally safer and smarter design. This really feels like it's opening up a whole new chapter for robotics. Instead of having to choose between a robot that knows a lot or a robot that can do a lot, we can finally have one that does both. It's a massive step toward those truly helpful robots we've always wanted. So I'll just leave you with this thought. If you had a robot that could keep learning forever without forgetting, what's the very first thing you'd want it to solve? All right, let's dive into one of the most exciting shifts happening in AI right now. We're talking about the move from AI that just, thinks and talks to an AI that can actually do things. This is the story of how AI is learning to get its hands dirty and solve real-world problems. I mean, we've all been blown away by AI generating incredible text, images, even code. But what if it could take that next giant leap? What if it could actually interact with software, search the web, and carry out a whole plan to book your vacation or debug a program all by itself? That's the huge question driving this next wave of AI development. And the answer to that question? Well, it's the AI agent. The easiest way to think about it is like this. For a long time, AI has had this brilliant voice, but no hands. An AI agent, well, it gives the AI a set of digital hands. It lets it use tools, click around on websites, and really interact with the digital world to get stuff done. And that gets to the core of what's known as the brain in a jar problem. Right now, we have these unbelievably powerful AI models. I mean, their reasoning ability is phenomenal, but they're kind of isolated. They can't directly act on their own conclusions. They can tell you exactly how to do something step by step, but they can't actually do it for you. So, how do we fix that? How do you get the brain out of the jar? Well, let's meet Longcat. It's a powerful new AI agent designed by a team of researchers to do exactly that, to break out and start acting. So its full name is, get this, Longcat Flash Thinking 2601. Yeah, we're just going to call it Longcat. It's an open source model from the Meituan team, and it was built from the ground up to master these agentic tasks. You know, the actions that finally bridge that gap between thinking and doing. And look, the results really speak for themselves. These are benchmark scores, and you definitely don't need to be a data scientist to get the story here. The green bars, that's Longcat. It's just consistently outperforming other top models in all the important skills, like coding, using tools, and searching the web. It's a huge step forward. Now, this kind of performance is backed by some serious horsepower. Longcat is a mixture of experts model, or MoE. You can think of that as having a whole team of specialized experts on call instead of just one generalist brain. And with a staggering 560 billion total parameters, this thing has the raw power it needs for some seriously advanced reasoning and action. Okay, so that's the what. The really big question is how? How do you actually teach a brain in a jar to act in the world? What's the secret sauce here? Well, it all comes down to a really clever training framework. The researchers themselves put it perfectly in their paper. The key phrase here is adaptive interaction. See, it's not just about thinking in a vacuum. It's about being in this constant loop of thinking, then acting, then getting feedback from the digital world, and then adjusting your plan. It is quite literally learning by doing. They broke down their training process into 3 big steps. First, they had a problem. There's almost no data out there of AIs interacting with tools, so they had to create it from scratch. Then they needed a place for the AI to practice, a massive one. And finally, they used reinforcement learning to hone and perfect its skills. So for that first step, creating the data, they used this brilliant hybrid approach. On one hand, they pulled from unstructured text, things like online tutorials. That gave them a huge variety of tasks. But to make sure the AI learned logical, correct steps, they also generated data from executable Python code. That guaranteed that every single action was verifiable and made sense. Okay, so now you've got the training data, but you need a place for the AI to actually practice. And we're not talking about one little digital sandbox here. To learn truly general skills, this AI needed a massive, sprawling digital playground, almost like a giant library of video games, where each game teaches it a totally different skill. And when I say massive, I mean it. The scale of this playground is just immense. They built over 10,000 unique training environments across more than 20 different domains, everything from file systems to retail databases. And at its peak, their system was running 32,000 of these simulations at the same time. The AI was just learning at this incredible pace. But here's the catch. Training an AI in a perfect, clean, digital world is one thing. But sending it out into the messy, unpredictable real world, that is a whole other challenge. See, in those training simulations, everything works just like it's supposed to. The tools are reliable, the websites load perfectly, the data is clean. It's basically the ideal scenario for learning the fundamentals. But the real world, as we all know, is full of errors. It's got unexpected API changes, laggy websites, noisy data, you name it. An agent that was only trained in those perfect conditions would just fall apart the second it hit a real-world snag. So the researchers did something incredibly smart. They deliberately messed up their own training environments. They systematically injected all sorts of noise and errors into the simulations. It's kind of like a flight simulator that doesn't just train a pilot for a clear, sunny day, but also for thunderstorms, engine failures, and broken instruments. It makes the final model way more robust and ready for anything. All right, and that brings us to the final key innovation here, a special feature that lets the agent basically think harder whenever it gets stuck on a really tough problem. The model basically has 2 gears. In standard mode, it works fast, finding a solution along a single logical path. But when you switch on heavy thinking mode, it totally expands its reasoning. It's like a chess master who doesn't just think about their next move, but explores multiple different strategies and all their consequences several moves ahead before finally picking the absolute best path. And the payoff for that is huge.
This deeper, multi-path exploration gives the model the extra oomph it needs to crack the most complex reasoning puzzles and agentic tasks, the kind of stuff that would totally stump other models.
So if you're going to remember just 3 things from all this, let it be these. First, the incredible power of scaling up the environment, using those vast digital playgrounds to teach general skills. Second, building for reality, training the AI with noise and imperfections to make it tough. And third, the ability to think deeper with a heavy thinking mode to crack the hardest problems. When you put it all together, the crucial point is this. We are really witnessing the evolution of AI in real time. It's moving way beyond being just a fancy text generator. It's becoming a true problem solver, a partner that can actually help us get things done in the digital world. And of course, this leaves us with a really fascinating and kind of huge question for the future. As these AI agents get even more capable and more reliable, what are we going to ask them to do next? What complex, messy problems that seem impossible today will become trivial for an AI agent to solve for us tomorrow?